Okay, so in lesson 11, we're not going to do a ton of calculations. We're going to do some calculations, and then it's a lot of, theoretical pieces as we kind of talk about heat transfer, just in general, what's going on, and how do we predict what's actually going to happen. A lot of the calculations with regards to heat transfer are way beyond what you'd need to be able to do in a high school level physics class, but having a good idea of what's going on is really, really helpful. So the homework questions from this section, other than one question that asks you to determine which one has a higher temperature, there aren't any calculations. It's more of like just thinking about it and getting a response down. All right. So first question we need to address is this. What is temperature? Notice I didn't ask what is the temperature, but I asked, what is temperature? How do we even talk, when we talk about the temperature of something, what do we even mean? And so what temperature is it's the average kinetic energy of the particles of the material. So if you say, this table's temperature is 72 degrees Fahrenheit, what you're talking about is the average kinetic energy of the particles making up this table equates to a measurement of 72 degrees Fahrenheit. But even our temperature scales are all relative, because our temperature scales aren't measuring kinetic energy. How do you know that? How do you know that degrees Fahrenheit is not measuring kinetic energy directly and is rather relative kinetic energy? What are the units of kinetic energy? What are the units of any energy? Yeah. Joules. Degrees Fahrenheit, that is not joules, right? Or degrees Celsius or Kelvin, however you want to represent temperature, that is not joules, meaning you're not directly measuring the energy, and instead it is a relative scale. And so Fahrenheit is based on the melting and boiling point of alcohol, and the Celsius scale is based on the melting and, you're welcome, the melting and boiling point of water. Okay, so those are relative scales measuring the relative kinetic energy, not the actual kinetic energy. If it was actually measuring the average kinetic energy, it would be in joules. Right? Cool. All right, so the actual kinetic energy varies from particle to particle. Notice temperature is the average kinetic energy, but some particles are moving faster than others. So it's the average kinetic energy. Inside there, Malachi is also a grade report. So your material in there is graded, and then there's a grade report for fall semester. You are very welcome. And so, again, the actual kinetic energy varies from particles to particles. So let's say the entire material, just for simplicity's sake, the entire material is made up of two particles. Okay? Entire material is made up of two particles. One of them has a kinetic energy of 5 joules. Okay? The other one has a kinetic energy of 1 joule. What would the average kinetic energy be? 3 joules, right? So we would do 5 joules plus 1 joule divided by 2, because there were 2 measurements, and we get 6 joules divided by 2, which equals 3 joules. So the average kinetic energy is 3 joules, but one of them has a kinetic energy of 1 joule, one of them has a kinetic energy of 5 joules. But what temperature is the average kinetic energy. But this is a reminder, and this is a very simple scenario where your entire substance is made up of 2 particles, but there's room for a lot of variation. There's room for a lot of variation. Okay, we'll come back to this idea in a little bit. So remember that kinetic energy is the energy of moving particles. It's the energy of moving particles. And so it's energy in motion. It's energy that actually most clearly can be used to do work, right? We saw this when we talked about a car moving at a particular velocity hitting an object. And so it's the energy that's most easily thought of with regards to work. And so if you're thinking about average kinetic energy and you touch something really hot, the average kinetic energy of that object is really high, right? And so that the particles are going to do work on your hand, right? By transferring some of that kinetic energy to your hand, which is going to feel hot when the particles that make up your hand start to increase in velocity. You're gonna feel that. All right, just some other bits of information as we continue to build on this idea. Gases and liquids. By the way, we collectively refer to gases and liquids as fluids. Liquids are fluids, gases are fluids. And they are not good conductors of heat. And the reason for this is the particles are really free to move around. And you're like, well, then shouldn't they be great conductors of heat because they can change their velocity quite a bit? Yeah, but the ability to actually interact with them and get the collision is really low, right? And that's what you need if you're going to transfer kinetic energy. We saw this with momentum, right? If two objects collide, the velocity of each of those objects has the potential to change as a result of that collision. Do you agree? We saw this in our lab. We saw this in our last unit. And so the reason why fluids are not good conductors of electricity or of heat, they actually are great conductors of electricity, some of them. But the reason why they're not good conductors of heat is because the probability of interacting with one of those particles is much, much lower. Okay? And so if they're going to transfer heat, they have to do it in a way other than by conducting heat. Yeah.
I've heard, I don't know if it's true, that many of the particles in space are actually quite hot. It's just there's so few of them there.
I believe that to be true. Yeah. I would believe that to be true, that the velocity, I mean, it has to be because the universe is expanding and it's expanding at an exponential rate. So every day that passes, the rate at which the universe is expanding increases, which means the materials making up the universe are speeding up every day. And so, yeah, absolutely, those particles have to be, really traveling fast, but there are so few of them that it's...
Feels freezing.
Yeah, exactly, because the chances of you interacting with one of those particles is just so small. All right, solids, on the other hand, solids are great conductors of heat because the particles are locked in place. And so it's really likely that you're going to be able to hit them and get these particles to collide and transfer their kinetic energy. And again, it's a little weird because you're thinking, well, if it's a solid and those particles are locked in place, how do they actually speed up? How do they actually speed up? And I'm going to present to you a statement in a minute once you finish writing down what you're doing. Is your mom coming, Malachi? No, is she hanging out in the car? Oh, she just, okay. All right. Well, I'll hold on to Isaiah's if she's going to pick you up though, right? No. Oh, wow. Just okay. Oh, okay. I'll hold on to Isaiah's. If she wants it, let me know or let her know to send me an email and I'll send her Isaiah's. All right. True or false? The particles making up solids move. True or false? So the particles within this tabletop are moving.
False.
We have a vote for false. Anyone second, third, fourth that vote? Any votes for true that the particles in there are moving? So we've got 2 votes for true. Do we have a third, a fourth, a fifth? Everybody else is going to abstain? Okay, they are moving. They are moving, and even though they're locked, so if they're locked in a crystal, and that's what solids are, the particles are locked in a crystal, they still vibrate, the individual atoms vibrate within that matrix. And so there's an average distance between any 2 atoms, but at any given moment, that distance may actually be further or they may be further apart or closer together than they were before. And so there is some vibration. Now, it's limited because they're still locked in a crystal, so you don't sense a lot of that vibration, but there is some vibration. And this is why when you heat an object like a tabletop up, it can crack, is because of those vibrations. They can get so strong that they start to break bonds and break that crystal apart. And so they are moving. And so even though the atoms within a solid are packed in a crystal, they still do vibrate around and they still have kinetic energy. And because the solids, two solids, if you take, this object, let's say I heated this up. By the way, for those of you that can't actually see what this is my pointer that I love so much. Let's say I heated this thing up and I set it on this cold table, right? The probability of particles from this pointer interacting with particles from this table, that's really high, right? They're in physical contact right now. And that's why solids are great conductors of heat. So if this is really hot, some of that heat is going to transfer into this table, right? Because the vibration of the particles in this solid are going to transfer their kinetic energy to something with less kinetic energy. Okay? Does that make sense? Is that okay? All right. So let's look at this. Explain which object has a higher temperature. A gas where the average particle has a mass of 0.000567 kilograms and a velocity, and this is an average velocity, of 7.56 meters per second, or a solid where the average particle has a mass of 0.000777 kilograms and it's vibrating with a velocity of 2.55 meters per second. Remembering that let's start off with our typical progression. What do we have or what are we given? We have two objects, right? Let's call them object A and object B for simplicity. Object A is our gas. Object B is our solid. Okay? And the mass of this gas is 0.000567 kilograms, right? And the velocity is what? Of object A? 7.56 meters per second. Object B is our solid. Our mass is a bit higher, 0.000777 kilograms. And our velocity is a bit lower, average velocity, 2.55 meters per second. And we're saying, okay, well, explain which object has a higher temperature. Well, our tools, we remember that temperature is the average kinetic energy. We have a tool for calculating kinetic energy. What is it? Kinetic energy is equal to 1/2 mv squared. 1/2 the mass times the velocity squared, or the square of the velocity. Okay. And what do we want? We want to know which one has a higher temperature, right? But in order to determine that, we need the kinetic energy of object A, and we need the kinetic energy of object B. Do you agree? Because if temperature is average kinetic energy, and this problem gave it to us with average mass and average velocity, we can use that to figure out the average kinetic energy, and then we can compare them. Whichever one has a higher average kinetic energy, that one has a higher temperature. True or false? Higher average kinetic energy equals higher temperature. True or false? That is absolutely true. Okay, temperature is the average kinetic energy relative, and so the higher the kinetic energy, the higher the temperature. Okay, the higher the average kinetic. All right, so for object A, we have 1/2 times our mass, which is 0.000567 kilograms, times our velocity, which is 7 0.56 meters per second quantity squared. Okay. Should have left myself some more space, but I didn't. I'm sorry. Hopefully you have more space than I do so your paper isn't ugly like this is. If it is, I'm sorry. You can blame it on me. If somebody looks at this years from now and says, why are your notes so cramped? Blame it on me. Can everybody read this okay? All right. So then the kinetic energy of object B is 1/2 times the mass of object B, which is 0.000777 kilograms, times our velocity, which is 2.55 meters per second, quantity squared. And now we can calculate this out. It is 7.56 squared times our mass, which is 0.000567 times 1/2. And we get that the average kinetic energy of object A is, our answer should be presented in 3 significant figures. This is 3 significant figures. This is 3 significant figures. This 1/2 is exactly 1/2. And so we get our average kinetic energy is 0.0162 joules. All right, our units are going to be kilograms meters squared per second squared, which are joules. Right? You okay with that? Okay, so now this one, 2.55 squared times 0.000777 times 0.5, and we get that the average kinetic energy for object B is equal to 0.00253 joules. Okay, which object has a higher temperature? Object A, with which is our gas, or object B, which is our solid? Which one has a higher temperature? A, because its kinetic energy is higher, right? This is 0.01, this one is 0.002. So this kinetic energy is about 1/5 what this is. And so relatively speaking, this has more kinetic energy, higher temperature. And remember, our temperature scale is not directly a measurement of the amount of kinetic energy, but rather is a assessment of relative kinetic energy. Okay? So does it make sense that object A, our gas, has a higher temperature than object B, our solid? Okay, cool. All right. So with this next question, this is just kind of a statement. Again, I told you other than doing this, what we do in this section is it's more theoretical. We're just kind of explaining what happens. So explain how an object heats up. So if an object heats up, what's happening to its temperature? Is it increasing or is it decreasing? It's increasing. And what is temperature a measurement of? The average kinetic energy of the particles in that material, right? So if it heats up and its temperature increases, what's going to happen to the kinetic energy of the particles that make up that material? Is it going to go up or is it going to go down? If the temperature increases, does the kinetic energy increase or does it decrease? It increases. Now, are the particles going to gain in mass? No, they're not, right? Particles do not gain in mass. We have the law of conservation of mass, right? So if the particles don't gain in mass, how is the kinetic energy going to increase? If you can't increase the mass, what do you need to increase to make kinetic energy increase? The velocity. So how does an object heat up? The velocity of the particles increases. Okay? That's how an object heats up. The velocity of the particles that make up that object increases. The velocity increases. Sorry, subject-verb agreement. Velocity is singular, increases. that make sense? Cool. Y'all have any questions about that? Because now we need to start talking about how do we transfer heat. Because you all have felt it, right? You've either, you've gotten out of a swimming pool, stepped on the concrete on a hot summer day, and you have felt energy transfer, right? Or, you've gotten out of bed in the middle of the night and stepped on the cold tile floor, and you have felt energy transfer, right? And so now we need to talk about the mechanisms behind how that happens. Okay? Any thoughts, concerns? Y'all doing okay? Seems a little glum. I think it's maybe because it's because we're missing someone. Isaiah's not here. He's in Taiwan. Yeah, he's really far away. We miss you, Isaiah, if you're watching this video later. All right. So our next question, second question, how does heat transfer? How does heat transfer? Now, we didn't talk about this next point when we talked about momentum, but this is something that just tends to be true of all collisions. So heat transfers from higher energy to lower energy. And so as two objects collide, the momentum tends to transfer from something with higher kinetic energy to something with lower kinetic energy. And so that just tends to happen in collisions. So, if you think about it this way, if two objects collide and one of them has a really high velocity, let's say the two objects are the same mass, okay? Actually, let's use this example that I had up here before, okay? So here's a material made up of two particles, and the average kinetic energy is 3 joules, okay? And let's say we have another material, also made up of two particles, but both of these particles have a kinetic energy of 2 joules, okay? So this other object, also made up of two particles, both particles have the same kinetic energy. What is the average kinetic energy of this material? If it's made up of two particles and both of them have a kinetic energy of 2 joules, what's the average kinetic energy? 2 joules, okay? So we have an object that has an average kinetic energy of 3 joules. We have an object that has an average kinetic energy of 2 joules. Which one has a higher temperature? This one here, right? Because its average kinetic energy is 3 joules, the average kinetic energy here is 2 joules. But let's think about this. What about if this particle collided with this particle here? Right? And so if energy tends to transfer from something with higher kinetic energy to something with lower kinetic energy, if these two objects collide, this one's going to slow down, this one's going to speed up, right? As they collide, some of the kinetic energy from this is going to go into this object, so this one's going to speed up, this one's going to slow down, okay? And so this is going to lose some kinetic energy, and some of that's going to be transferred to this particle, even though this material has a higher temperature than this one. But the individual particle by particle transfer of energy would be from this particle to this one. But what about if this particle, the 5 joule particle, collided with one of these? Energy is going to transfer from this into this, and a lot more energy is going to transfer here than what transferred from here to here. So overall, and again, when you have a 2-particle material, that's weird, right? What material is made up of only 2 particles? But when you have this setup, there's a lot of variation of what could happen. But overall, if these two objects are in contact with each other, so all these particles should interact, eventually it's going to get to a point where everything in there has the same kinetic energy. Everything in there has the same kinetic energy. The same average. So that object A, whatever this is, will have the same average kinetic energy as this object here. Okay? But when any two particles interact, whichever one has more kinetic energy is going to give some of that energy to the one with less. Okay, so that one's going to slow down, the other one's going to speed up. Because you can't change the mass, right? Unless, of course, when the two particles collide, they become one object. But in which case, something weird happens anyways, right? An elastic collision. All right, so this happens in three ways. One, as conduction. So conduction is as heat moves from one solid to another as the particles collide. So in this case, in conduction, your two objects are in contact. This was my illustration earlier, right? I heat this pointer up. I set it on this table. The heat's going to transfer from my pointer to this table by conduction. Two solids in physical contact. Is that okay? Now, true or false? If you heat the ground up, the air above the ground heats up as well. True or false? True, right? Let's think about this. Let's say you light something on fire, right? You build a nice fire pit, you've got a piece of wood, you light it on fire. That piece of wood is getting hot, right? It is on fire. The air around that piece of wood, it heats up too. That's just why it's nice to sit next to a fire, right? But if a fluid that is a gas, the air, or a liquid is not a good conductor of heat, it's probably not by conduction that it's heating up, right? And so we have another type of heat transfer called convection. And convection is heat transfer by moving fluids. And so as heat transfers into a fluid, same thing happens as heat transfers into a solid. The particles speed up. But as these particles speed up, they get further apart. And that fluid becomes less dense, right? If things are further apart, it's less dense, right? You think of something being dense as a whole bunch of material packed tightly together. That's how I think of something being dense, right? And so if they're moving faster, they're going to get further apart. It becomes less dense and it actually rises. So you ever heard that heat rises? It's actually more properly said that a warm fluid rises. And so a fluid that is warmer, has more energy, is going to be less dense, and that's what's going to rise. Okay? And so convection is heat transfer either into a fluid or from a fluid into another object. Okay? And so as you're sitting by a fire, heat transferred from that burning wood into the air, and then heat's going to transfer out of the air into your body. But it's not going to be by conduction, by two solid objects being in contact with one another. Instead, it's going to be by convection. But overall, it's still going to require bombardment. It's still going to require collisions of individual particles. Okay. Make sense? All right. And then the last one is by radiation. Radiation as light particles, we call these photons. An individual light particle is called a photon. So radiation or radiative heat works as light particles, photons, collide with objects. All right. Now, all objects radiate energy. Every object, doesn't matter what it is. You radiate energy, which means you're releasing light, that those light particles can go and collide with other objects and transfer their heat. How do I know? May I use you as an example, Zion? Okay. How do we know that Zion is radiating light? How do we know it? Can you see Zion? Yes, you can, right? So he's at least reflecting light, but that's not exactly the question, right? So most of the reason why you can see Zion is because he's reflecting light. He doesn't absorb all of the light that hits his body. He reflects some of it, and so you can see him. But how do we know he's also radiating light? Have you ever seen thermal imaging? So thermal imaging looks for objects radiating light, and everything radiates light. And so even if there were absolutely no light hitting Zion, And so he wasn't reflecting any light off. But you looked at him with a thermal camera or a thermal image, you'd see his shape. You'd see Zion because he's emitting light. And I don't know if you've ever seen thermal images before, but you probably have in some context. And so everything, no matter what it is, it radiates light energy. Unless you took it to what's called absolute zero, which we'll talk about in just a second. So two objects in contact will tend to reach thermal equilibrium. So again, if I heat up this pointer, I set it on this table, they will tend to reach thermal equilibrium. They'll get to a point in which both objects are at the same temperature. The average kinetic energy of the particles in both objects will be the same. Okay. So two objects in contact will tend to reach thermal equilibrium. Yeah, it's true. Also, an object and the surrounding fluid will tend to reach thermal equilibrium. Objects and the surrounding fluid will tend to reach thermal equilibrium, meaning this table and the surrounding air will tend to reach thermal equilibrium. But we kind of do some interesting things in that we can heat the air, we can cool the air, and we can make it hard for this tabletop to catch up, right, as we change the temperature of the air that we're blowing into this room. In the morning, the air blowing into this room is really hot. Now during the day, the heater's not really on, kicks on every now and again. Okay, but an object and the surrounding fluid will tend to reach thermal equilibrium as well. And then finally, objects will always radiate heat unless they are at what's called absolute zero, which happens to be negative 273.15 degrees Celsius. Negative 273.15 degrees Celsius. That's really, really cold. The reason why we call it absolute zero is because at that temperature, there is zero kinetic energy of the particles in that material. All motion stops. All motion stops. But what's interesting is you actually cannot keep an object at absolute zero. Because if you got it to absolute zero, which we have machines that can do this, as soon as you take it out to try to record its temperature, it warms up, right? And actually gets some energy from the surrounding fluid. And so there's nothing really at absolute zero. Even empty space is not at absolute zero because there are particles in it that are moving. Okay? But at absolute zero, all motion stops. And if there's absolutely zero kinetic energy of the particles in that material, then it's at absolute zero, and it will not radiate light energy. But if it's not at absolute zero, which nothing is, it's going to radiate light energy. Now it will show up as different intensities, depending on how much energy you're releasing. The hotter the object, the more light energy it's going to release, but everything's going to radiate energy. Yeah, Josh?
So what if it goes colder? It just stays the same still?
If it goes colder, what do you mean? In terms of the amount of light it radiates?
Like it just is basically that point, and anything colder.
Yeah, it can actually be any colder because remember, temperature is a measurement of the average kinetic energy. So if the kinetic energy is zero, you can't have negative kinetic energy because kinetic energy is energy of motion. So you actually cannot get any colder than negative 273.15 degrees Celsius. There's no limit to how high the temperature could get. I mean, at a certain point, everything just becomes like a thermal meltdown. But it's not limited in the same way that the lowest temperature. Since temperature is just a measurement of the average kinetic energy, if you have zero kinetic energy, that's as low as you can go. Because there's no such thing as negative motion. Does that make sense? Okay, so if two objects collide, what's going to happen? Yeah, the energy is going to transfer, right? And typically the object or the particle with more kinetic energy is going to give some of its kinetic energy to the other particle. All right? Sound good? Okay. So first question that we're going to talk about together, demonstrate the three types of heat transfer. Demonstrate the three types of heat transfer. Some of these I've already alluded to. Okay? So you heat this object up, right? I mean, we could ask, how'd you heat it up, right? Did you put it in a hot fluid and then it was heated by convection, right? Or did you like set it on something that was on fire, in which case you heated it by conduction? But either way, you heat this object up, you set it on this table. This pointer is now going to donate some energy to the table. It's going to heat it up by conduction. Okay, I heat up this pointer. I hold it here by my foam handle that hopefully is not as hot as the metal is. I heat this up. I hold it like this. It's going to heat the surrounding air by convection. Okay, and then as you look at this with a thermal camera, even now you would notice that it is radiating thermal energy. It is radiating light. And that is an illustration of radiative heating. And so that light has the potential to bombard, an object and actually heat it up. And that's why when objects get really, really hot, like red hot, they actually emit very obvious light, right? Sound good? Okay. All right, here's our next one. This is a fun one. So two objects are touching one another. Two objects are touching one another. Look at this. Two objects are touching one another. Remember that time last semester where I just kept dropping this to illustrate free fall? Do you remember that fondly? I remember that fondly. I hope you remember most of our times together fondly. All right, so object A has a temperature of 45 degrees Celsius, which I think would be about 110, maybe even 115 degrees Fahrenheit. So that'd be pretty hot, but not too hot to touch. Okay. So object A has a temperature of 45 degrees Celsius. Object B has a temperature of 25 degrees Celsius. Will any of the particles from object B transfer energy to a particle from object A? So let's think about this. Object A has a higher average kinetic energy than object B. Yes? How do we know? How do we know that the average kinetic energy of object A is higher than the average kinetic energy of object B? Because its temperature is higher. Okay, but remember, average kinetic energy is just average kinetic energy. There's a variation in the actual kinetic energy of the particles, just like our example here. So will any of the particles from object B, which is colder or cooler, actually transfer energy to a particle from object A? What that is asking is, are there any particles in object A, in object B, the colder object, that are moving faster than a particle in object A? In terms of average, object A has a higher average kinetic energy, right? But average is just average. Not every particle is going to be average, right? Just like not every human being has average height or average eye color, which eye color actually does come in averages because it varies like height. But anyways, that's another story for another time. Or average intelligence, right? Not everybody is average. There are some people that are average, and there are some particles that would be average and have the same amount of kinetic energy as the average, but some are lower, some are higher, right? So will there be some particles in object B, the colder, that have higher kinetic energy than a particle in object A? Almost certainly. Almost certainly. Is it conceivable that that wouldn't be the case? Yes, but that would be really strange, right? Does that make sense? So object A has a higher average kinetic energy than object B, but in terms of various particles, it shouldn't surprise you to find some particles from object B, the cooler object, that when they collide with an object or a particle from object A, they actually give off some kinetic energy, that they had a higher kinetic energy than that object. Okay. We okay with that? So again, I told you, today it's just theoretical. It's a little weird, a little strange. Next week, don't worry, we'll talk about entropy, the second law of thermodynamics. You'll love it. Entropy is a measurement of randomness. We'll talk about the second law of thermodynamics and how energy tends to flow, and we'll connect it back with this one. All right. So our last question that we're going to deal with together. If two objects are in thermal equilibrium, will any particles collide and transfer energy? So if two objects are at thermal equilibrium, that is, the average kinetic energy of this pointer is equal to the average kinetic energy of this table, will any of the particles from this pointer still collide with particles of the table and transfer energy? What do we think? Okay, why not?
Because they've got equal kinetic energy.
Equal average kinetic energy, right? So even think about this. Even within the same object, there's variation in the amount of kinetic energy, right? Right? So even if they're in thermal equilibrium, that is, they're at the same temperature, there's still going to be some particles that are holding out, right? They want to be different. They want to express themselves in a different way. And so their kinetic energy is a bit unique. And so even if two objects are in thermal equilibrium, there are still going to be some particles in those objects that have higher kinetic energy than others. The only way to ensure that that will not happen is to take the two objects to the absolute zero, where there's no movement. And then there's no variation. Every particle is standing still. And that's the only point at which you can ensure that. It is if they reach thermal equilibrium, and that thermal equilibrium is absolute zero. All right. Any questions about this material? I know it's a little bit different. We haven't done a lot of problem solving. We really only did one problem together where we brought back kinetic energy that we've talked about before. Any misunderstandings of energy? Have you learned anything new about temperature and kinetic energy today? Cool. Can't ask for much more than that. Alrighty, well, if there aren't any questions, y'all are free to go. If you have any questions about your grade reports, feel free to ask those. If you want